Dear all, just to inform you that we are now online, and then the room is open, and then we will start the webinar soon.
I would say the space industry is quite active and quite special.
There is no job where you don't have multidisciplinarity. You have to be curious and to not just do what people ask you to do.
Every day I start working on communicating a new project. It's a completely different work for me.
Every field you can imagine, you can find a way to have an impact in space exploration. The number one difficulty is to find what you really like and what you really enjoy. If you found what you like, then the most difficult step is already done.
So really, go for it. There's something in space that I think unites people. There's lots of countries involved there, and they all work together amazingly well. I think it's way more important than we realize. I'm hoping for a bit more women in the space industry because we are not that many, and sometimes when you see panels, it's all male, and you think, okay, aren't there any great women? And yes, they are. So I'm hoping for a more diverse space community.
And to go further to the moon, to Mars, and so on.
We really produce something which people want. The data our satellites deliver to our end users is something which makes a difference even to everybody's daily life, because every weather prediction you see on your smartphone, on the TV screen, does rely on the data we deliver. And being part of that process, of that organization, is great. My job is to make sure that the original user requirements of the National Weather Services are finally being met by the satellites being flown in space. A user requirement could be, for example, a high-resolution wind speed. And requirements engineering makes sure that the final satellite, the instrument, the ground processing all work together such that the wind speeds which are produced meet the requirements of our users. I think Darmstadt, and especially the area, offers a lot for work-life balance. You can go, in 20 minutes you are in the middle of the Odenwald, in the forest. You can go hiking, you don't see anybody. I personally do a lot of mountain biking there, and I can even cycle to work. And on the other hand, if you want to see city lights, you drive 20 minutes and you're in Frankfurt. And if you want to go even further, you're at the airport and you can basically fly everywhere from there.
I work at EUMETSAT as a remote sensing scientist, and my focus is on sea surface temperatures and sea ice surface temperatures from satellites. So I've always been interested in science and the environment, but I wanted to do something that meant something and that actually helped people. So working at EUMETSAT gave me the opportunity to combine all of these different interests. I think the job I do here makes a difference in the world, as well as affecting weather forecasts. It's also important to understand a changing climate. So we need to know the best possible knowledge of our ocean and the ocean's health so that we can monitor it and then understand how this may change in the future.
So the most exciting and rewarding part of my job is obviously when we have a launch and we get the first telemetry into the ground segment we just built, and we have the first payload telemetry coming in and the first products coming out. This doesn't happen every year, but we are working several years towards such a target. I believe the job I do makes a difference, especially when you watch weather forecasts on the TV in the evening, which is made with images or data we provide from EUMETSAT. And also, for example, in the recent hurricane events in Florida, we provided support to NOAA to do their own forecast and see where the hurricane would go. So I really think it makes a difference.
Since the 1980s, OIP's Sensor Systems has been an electro-optical partner for ESA. OIP developed custom-made high-performing optical payloads to provide images of planets in renowned missions, such as Proba 1, Mars, and Venus Express. Our compact visual monitoring cameras are used to monitor the effective performance of space mechanisms and to make scientific images to be studied down on Earth. OIP's spectrometers support ESA and other space partners in planet observation missions, such as Proba 5. Those spectrometers are also used by scientists to analyze the Earth, Mars, and Venus atmosphere on board of Altius, Nomad, and Soir. If you are looking for high-performance visualization from Earth to space, OIP is your partner by excellence.
Space is part of our lives today, bringing many benefits. In the near future, space will become an even more important part of our lives. Bringing these benefits to us requires numerous technologies to work together. Space Application Services has been developing and delivering technology-enabled services, bringing the benefits of space to Earth for more than 30 years. We plan, prepare, develop, and operate equipment in space for our customers, such as the European Space Agency and NASA. Our strategy is to identify the right question, do the research, and develop the most suitable business solution. Today, we already provide anyone regular and frequent access to space. We open the door to research and manufacturing of novel products that do not exist on Earth. We train the astronauts of tomorrow, and we keep those working in space healthy and safe. We provide provide technology for in-orbit construction of low Earth orbit space stations and platforms. These will be the industrial powerhouses driving tomorrow's emerging markets, providing advanced materials and medicines. In the next decade, not only will we harvest the resources that are plentiful in space and which are depleted or scarce on Earth, but human settlements in space will use these resources to sustain their independent lives. Our technologies are improving life on Earth by predicting space weather events that can damage our electricity grids. Our astronaut exercise devices help to rehabilitate injured persons, and our robotics replace humans in hazardous environments. This is the near future. Space application services will be a part of it. We'll be happy to work on this future with you.
Travailler au pôle spatial Rue du Transine, c'est faire partie d'un espace de travail stimulant offrant de nombreuses opportunités professionnelles. Milieu à haute plus-value, le pôle accueille des entreprises internationales dédiées aux applications spatiales. D'un côté, le centre ESSEC de l'Agence spatiale européenne à Redu. De l'autre, le parc d'activités économiques de Galaxia, développé par Idelux à Transine, qui comporte un centre d'entreprise, un incubateur de start-up, l'ESSEC Galaxia, l'Eurospace Center, le Galileo Integrated Logistics Support Center de la Commission européenne ou encore Vitrochitset. Ingénieurs, équipes pluridisciplinaires, start-ups et étudiants, des hommes et des femmes venus du monde entier s'y côtoient chaque jour au sein d'infrastructures modernes et innovantes, d'où naissent des projets de grande envergure, comme la gestion de l'opérationnalité des stations du système Galileo. Travailler au pôle spatial Rue du Transine, c'est faire partie d'un espace de mobilité situé au cœur de l'Europe. Entouré de grands axes routiers et le long de l'autoroute E411, le pôle bénéficie d'accès fluides et rapides depuis Namur, Bruxelles, Luxembourg et tous ses environs, en voiture et via les transports en commun. Travailler au pôle spatial Rue du Transine, c'est faire partie d'un espace authentique et naturel. Lieu de gastronomie et de patrimoine, la région entourant le pôle offre des occasions de sorties variées, telles que le festival de Chasse-Pierre, la foire agricole de Libramont, Libin et son musée Mudia, ou encore le village du livre de Redu, ses infrastructures sportives modernes, son cadre naturel propice aux balades et ses nombreux lieux touristiques comme Bouillon, Bastogne, Durbuy ou encore La Roche en Ardennes. Travailler au pôle spatial Rue du Transine, c'est faire partie d'un espace culturel porté par de nombreux centres urbains rapidement accessibles. Namur, Luxembourg, Liège, mais aussi Marches, Rochefort ou Libramont. Situé à seulement 40 minutes du pôle, Namur propose une vie citadine dynamique et de multiples activités culturelles, musées, théâtres, expositions ou encore concerts. Travailler au pôle spatial Rue du Transine, c'est faire partie d'un espace de vie de qualité pour développer un réseau de connaissances et fonder une famille. Logement à prix accessible, proximité de centres hospitaliers ou encore universités, haute école et écoles internationales sont autant d'atouts essentiels pour le bien-être des habitants de la région. Vous aussi, faites partie du pôle spatial Rue du Transine. Rendez-vous dès maintenant sur investinluxembourg.be.
My name is Nicolas Hartmann. I've been working for 3 months here at Vitro-CZ Belgium in Transin as a ground system engineer.
My name is Lise Mouton and I am a recruiter and employer branding at Vitro-CZ Belgium.
My background is engineering for 5 years, and the purpose of my job is to be sure that there are not any issues with the infrastructure on the Earth for the signal coming from the space.
Well, my background is a bachelor degree in human resources management, and I joined Vitro-CZ Belgium 2 years ago, firstly with an internship of 1 year and now for the undefined contract.
I chose Vitro-CZ because I really wanted to work in the field of space, and after my master thesis they asked me if I wanted to join the team, and I said yes directly.
First of all, I was afraid because I didn't know nothing from the space domain, but all the colleagues explained me their job, the duties.
I loved space for a long time now, so I wanted to work not only for patients, but to work. Every day is different because you don't know what really you have to do. Sometimes you have to plan to go on travel somewhere. Sometimes you have to work on a project.
I chose to join the company because they were open to have a junior profile.
What I really like here, it's a family-sized company, so it's not too big. So it's really easy to talk with people if you have an issue or something.
Everyone knows everybody. We are around the same age, and there is a good atmosphere, good ambience.
They have strong knowledge in the Galileo program, so for a young engineer as me, it's really interesting.
It's exciting to work for a space company. Everyone can have an access to join the space domain, so why not you?
Space and its exploration has fascinated humans since centuries. We send a few space probes in the solar system. We have even sent robots and rovers on Mars surface to explore it. And we even had a few city trips on the Moon. We also have people living in space in the International Space Agency every day since a couple of years now. But the next step, the step further to learn more about space, is definitely to go on Mars and to have manned exploration of Mars. How easy is it? Can we just take our lunch packet with us and go on Mars? No, definitely we cannot do that. Because we need, for our life, oxygen, water and food. And those elements represent massive amount of weight that we cannot just send on Mars. So we need to recycle the true waste to be able to sustain their life during space exploration, long-term space exploration. And this was the idea that was developed in the MELISA project by the European Space Agency 25 years ago now. In the MELISA project, the scientists are trying to build an artificial ecosystem that will allow recycling all true waste, urine, CO2, but also fecal materials if needed, to produce oxygen, water and food to sustain life of crew during years of mission. In the University of Mons, we are working on oxygen production based on cyanobacteria using different nitrogen sources. The University of Mons also participate to this space exploration and try to develop new methods to follow and optimize oxygen production by those microorganisms. Those projects also have a lot of application on Earth, because treating nitrogen waste, urine for example, using cyanobacteria is also a major challenge for space, but also for Earth application. If you want to learn more about this, just follow my talk about the MELISA project and the human's implication in producing oxygen in space using cyanobacteria. See you.
So I come to you to ask some questions. And I would like, please give your name, what you are doing, and why you are here in Switch to Space.
Cannot touch the mic. Okay, sorry. Hello, my name is Geoffrey. I'm a PhD student in his last year. So I came here to see a bit what are the different possibilities that I can have in the space domain. And yeah, so get to know more about the sector.
You have not choice your future career.
I have no choice.
You didn't choose already your career in the future. What you want to do?
So it's very vast, I think, and yet I'm still not confused, but I still don't know exactly in which field or which topic I want to work on. So
maybe space. Space,
yes, but in which particular application for space?
So that's the reason we organize Switch to Space. Hi.
Hi.
What is your name?
Miriam Cisneros. I'm a PhD student. This is my third year in Louvain-la-Neuve, working in collaboration with the Aeronomy Institute for Space, Aeronomy Institute of Belgium. I'm working in already space application, so I'm sure I want to continue in this area, and I wanted to see which other options exist to continue developing technology for space.
Okay, thank you. Thank you. And you?
I'm Andreas Luits, and I'm following the Master of Space Studies in Leuven, and that's why we were invited to this event.
Okay, and so why did you come here?
Because I'm interested in the topics of the talk.
Okay.
So I have no specific plans for the future.
Okay, you have to find it earlier. And you?
My name is Bas van Loo, and I'm also in the Master of Space Studies in Leuven. And yeah, I'm interested in working in the space industry, so that's why I came today to see what kind of things in technology sector are possible.
Okay. Okay. Yeah.
I would like to work on engineering applications. So, for example, satellite manufacturing or some other things. Yeah.
I come to you because it's interesting. You are not you are a young professional.
Yes.
But you are not working in the space sector. So.
Indeed, I'm working in the social entrepreneurship sector, and I am here because it's very interesting for me to follow up what's going on in the space sector, to widen my mind and to see what's going on in the world. Okay. Because it's a lot of innovation and technology that's very useful here on our planet as well.
Great, great, thank you. And you? I see the time, yes.
I'm Ott van Esdijk. I'm an industrial designer, and I'm also following the Master in Space Studies. And I'm here because I'm interested in the space industry in Belgium and also in Europe. So.
Okay, and to make networking with the space experts.
Indeed, yeah.
Okay, fine. And you?
I'm Cedric, and I'm also doing the Master of Space Studies program, like quite some people here. And I'm interested in technology, and especially space technology. Okay. And that's why I'm here.
Okay, which year you are?
Yeah, it's a master's after master's project.
Great. So. Great, a lot of brain here.
Hi, I'm Ulrich, and I'm also in the Masters of Space Studies. And I'm interested in space, and especially I want to know what are the players in Belgium and both in Europe for space technology. And I have a background in electronics. And my reasoning is that if you can make electronics for space, then you can make electronics for anything. So.
Great.
Yes.
Great. Thank you. And you?
I'm Christine Peters, and I'm also in the Master of Space Studies. And yes, I'm interested in space science and technology. And so, yes, the lectures here will be very interesting to hear so.
And you think to work in the space sector?
Yes, that would be very nice.
Okay. And you?
I'm Caro, and I'm also of the Master of Space Studies, and I am interested in project management. And I remember that there are two project managers here, so I'm looking forward to talking to them later.
Okay, fine. I would like to ask you, did you come for the switch to Space 1 in 2018? Some of you? No? See, I see fingers. Yes, okay, fine. And you?
Hi, my name is Tim. I'm a legal professional, and I took a break to take the same course, the same master's course as the other students here, because I want to be involved in future space law development. So.
And what are you doing now?
I'm studying the Master of Space Studies in Leuven, at KU Leuven.
Okay, that's
but
great.
It's going to be multidisciplinary, so I should be well aware of the technologies and the science behind it as well.
It's important for the future.
True.
Yeah. Thank you, thank you, thank you very much. So I'm looking for the timing, and I come to Stijn. Stijn. Hi, it's so long. You are a member from Space for a long time. Huh?
It's indeed a long time. So. Yeah.
And you are still with us for the second switch.
It was fun. It was fun the last time, so I like to come back. Yes.
Okay, and so don't explain what you will speak about it. We will say after.
We'll do that later.
So
yes.
Maybe about your path.
My past. I wasn't really passionate about space in the beginning, but I went to the Eurospace Center as a kid in Transin, very close to Rudu.
Yeah.
And I was there for half a day, and I thought this would be nice to do as a summer job. So I asked, and they said, you speak Dutch? Yeah, we have a lot of Dutch tourists here, which come in the summer, so we need people to guide them around. So I worked there for 7 years, and that's my way into space.
Yeah, great. And you, explain me, what did you? What is your path?
I started actually with a master studies, or a bachelor and master studies.
And how did you come to this master study?
I did not know what to do. I mean, physics is interesting, biology is interesting, but space is more interesting. So for me, it was a logical choice. So I went to Delft University in Holland to study space there. So, and I've been in space ever since.
Okay, that's easy. Thanks. And you, Philippe? How did you come to space? And what is your path?
My path is quite a long one. So to make a long story short, I started in Liège, the University of Liège, and then CSL. And then I moved to the Netherlands, European Space Agency, for a few years. And after that, I moved to Kourou in French Guiana. But this was public sector, so I wanted to try private sector. So I did an MBA, and then I moved to France, Air Liquide and Alstom. And I came back to Belgium 5 years ago as the CEO of AMOS. So I will tell you a little bit more about that later on. So it's a long story.
Okay, and at the beginning, why did you, what's happened to be interested in space?
It's difficult to say. I think maybe it started when I was 3 years old, and my father woke me up on 21st of July, 1969, to see Neil Armstrong landing on the moon. So that's probably the start of the story.
Yes, sure. Okay. Well, I think maybe Carl-Henrik, you will be one of the switch leaders for the topic 4, but 9. Let me say, tell me, why did you come to space?
So I started with finance, but someday I bought a telescope and started astrophotography. So I had some sort of epiphany. And so I moved from finance to astrophysics.
It's completely different. Huh?
Yeah, quite different, yeah. It's not about money, it's about discovery.
We will have the opportunity to speak about that later. And you, Marta,
so
how did you come to space?
I studied linguistics, which doesn't have to do a lot with space, and then I discovered space. So I attended the Space Studies program at International Space University, and that helped me a lot. And then I got into the sector, and I started working as marketing and communications officer at QinetiQ.
So that's great. So I think it's time to begin. Well, I come to space. I'm not really. There's no reason to come to space, but I read one day in a newspaper in province of Luxembourg that there is the fusée Europa 2, the rocket Europa 2, in a little way, and I go with my children to see the rocket. And I was so astonished because this rocket, maybe it would be better like this, because this rocket was in the country and there are cows eating grass around the rocket. I said, my God, this rocket must go to the moon and turn around the Earth. And then this rocket is there and cows are eating around it. And so it was so amazing. And so little by little, I was interested by space. Well, that's the story. So I will introduce Switch to Space for
all the followers. So good evening again to everyone, wherever you are, be it in Belgium or somewhere else in the world. And I checked this morning, many of you are coming from also from very far countries. There is Nepal, South Africa, Peru, Uganda, Japan, United States, and many other European countries, of course. And this is great, really, this is great because space links us beyond the borders. So, as I said yesterday, this evening, is of course making for you. We made it for you, young professionals and students, because we have been into numerous universities with space experts, and there we realized that you love to see launching of new spacecraft. You love to see a picture or movies on Earth, from Earth. You love to see astronauts working on a rocket, but you don't think to work in the space sector. And this is really strange. This is really strange. And it's also unfortunate because the sector is in good shape and continue to actively recruit. Yes, it's most are engineers, but it's so strange that you are not interested by the space sector. So where is the problem? Why is it like this? And I see personally two reasons. Because you are attracted by space, but you don't work in the space sector. Where is the reason? So the first reason for me is that the sector is too discrete and is living too much into its inner cycle. And it is very, very important. The second one, the career perspective within space greatly expand today into numerous fields. You have agronomy, you have medicine, biology, economy, defense, security, law, application, and the diversity of its scope is not yet well known. And it's still difficult for students to find an overview of the numerous possibilities of jobs in space. That's the reason why the super Belgium Switch team decided to launch the second edition of Switch to Space. Switch to Space is an event organized on 8 days with more than 40 experts, and today it's the day 3. And the topic is about out this world technology. So we are, today I think there are 297 followers. So this is very, it's a lot of people. And the speakers will share with you their expertise, explain various opportunities of career prospects in space. They will share insights into the individual path, their job, their vision of the future of space in an accessible way, just to help you to find the best way for your future career. But keep this in mind, keep it. In the next future, most of the job will be linked to space. And yes, Switch to Space, definitely it's the key that opens the path of the possible. Make your professional life exciting and enjoy Switch to Space. Thank you. And I will present Marta. We have already, we spoke a little bit before, but Marta. So I take my glasses for Marta. So Marta is Marketing and Communication Officer at QinetiQ after working in a new space startup. And she's an alumni of the International Space University, ISU, and one of the co-founders and team members of the Space. She is very active in the young space community. She has supported and organized various events like Space Hub and is an active member of the Space Generation Advisory Council, and she is our switch leader for the topic 3. So Marta, I give you the floor.
Thank you, Dominique. As you all know, Dominique is an experienced politician. She has been for 27 years in politics, marked by an active involvement in the space sector. In 2014, she launched U-Space in order to link students to Belgian space experts. She is currently the chair of U-Space, and she's also the chair of EURISTI, a board member of Vitrocizet Belgium, a member of the advisory board of ESPI, and the vice president of the International Astronautical Federation. Thank you, Dominique. Now I'm going to introduce the chair of our session, Michael François. He's joining us remotely. Michael holds a master in electromechanical engineering from the University of Louvain-la-Neuve and has been active in space for 20 years, 8 of them in the Belgian sector. He joined the European Space Agency Technology Center as project controller for small technology mission development, in particular, the first accurate dual spacecraft formation flying mission. He moved to optical instruments development management for Earth observation missions. He was also in charge of the vegetation payload on board the Probe B Belgian satellite. And now he is managing the development of the FLORIS instrument on board the ESA mission named FLEX, Fluorescence Explorer. So without further delay, Michael, the floor is yours.
Okay, good evening, everybody. Or maybe shall I say good morning, because if I could hear that we have students from all over the world. So good morning or good evening to everybody. So thanks for this nice introduction. Thanks to Dominique and to Marta to organize such an event to get connected the future young professional with the professional sector. So on my side, I don't have a nice story like I could hear from Stijn or Philippe, how they get to know from space or why they started to work in the space sector. For me, I started by chance. I mean, I had no idea, as you explained, Dominique, I had no idea it was possible to work in the space sector. So after my engineering degree, I didn't know that it was possible to work in space. And basically, I started really by chance. My first job was in the space, and I love it, and I never wanted to stop it. So I think this event like today is really a great opportunity to indeed to put together the students, the young professional with the space sector, because the space sector is in good shape. There is a lot of missions going on. And I think if I may complement what Dominique was saying in the introduction, today what we have is in the past, let's say in the last 20 or 30 years, space was dominated by the public sector. But what we see in the last 3-4 years, and really now it's really booming a lot, is really the private sector in the space start really to boom. I mean, I think everybody learn about SpaceX and so on. So there is really a booming of the space sector. So we need people, we need young people, and thanks to this event, we can talk to them. So thanks, Dominique, and all to the organizer of this event. So today we are going to talk about space technologies. I'm sure that if you ask the people in the street what they think about space, and they will always tell you that this is high technology, this is a high technology, which is partially true. I mean, I can talk from mission we do at the European Space Agency. It's always a mission which has never been done, or it is always a mission trying to do something better than what has been done in the past. And by better means more accurate, with new measurements and so on. And that means new technology. That means better mirrors. That means lighter structure, better electronics. I could hear electronics from one of the students. And this is indeed high technology. But one of the difficulties of space is that the space environment is one of the most difficult environment. We have heavy vibration during the launch, we have heavy shock, we have an acoustic environment very difficult to sustain. And then once we survive all that, we are in space and we have a lot of radiation. And so it is not only high technology, we need also to have a lot of inventiveness, I would say, to make sure that this technology can survive the space environment. So today I'm pleased to introduce 4 very different topics, which will be given by the speaker tonight. You will hear very, very different topics. So I had the primer to look at the presentation before, so I could go through it. And it's very interesting for everybody. So you will, I make a short introduction of what you are going to hear tonight. So first you will have a speech from Mattias, who is working at Antwerp Space in Antwerp, as it is obvious. And he's in charge of the communication system for the JUICE spacecraft. So the JUICE is one of the key future missions from ESA, from the Cosmic Mission, Vision program, to look at the Jupiter. And he will explain how difficult it is to communicate with the spacecraft at such a long distance. So a very interesting presentation. Then a completely different topic, Stijn will address the moon. So you hear the moon a lot. I think this is probably one of the topics you hear the most in the media. If it is not Mars, it's the moon. And Stijn will introduce a little bit what are the different critical systems we need to go back to the moon. Some of them exist already, so we have some of them, the technology is there, but some of them not. And Stijn will give you a good explanation on that. Then we will have Philippe talking about optics, and this is a domain I know very well myself. So I will give you a broad, let's say a large overview of the need of optical instrument on the ground for ground telescope, which is also very important, but also for space, for science mission, big telescope for science mission, but also a lot for Earth observation, because as you know, with the climate change, the Earth observation is really a critical domain for science and for weather forecast. And so Philippe will give you a large overview of different missions we have and a lot of technologies developed in Belgium. And then the last one, interesting talk, not really specifically on technology, but it will be given by Rutger, who works at OIP in Oudenaarde, who will talk about, let's say, the different phase of a project. I think this is probably something which is not known for the student, but when we design a space mission, we go through different phases and very different. So we start from the drawing, of course, and then until the end, we have the spacecraft ready. And this we go through a very specific process. And this you will get this nice introduction. So I think, if I'm not wrong, and Marta, correct me if I'm wrong, the first topic is from Mattias, is it correct?
Yes, that's correct.
So for the question, we propose to keep, there will be a question and answer at the end. If I see that the timing allows it, and I see, and you ask question on the chat, and I see some interesting question, I might ask it at the end before between the two speakers if we have time. Otherwise, we will keep them for the end. Okay, so I think it's at the end of my introduction. So I leave the floor to Mattias. So I introduced already briefly him. So I had the pleasure to work with him, by the way, in the past. So he's working in Antwerp Space, who is in charge of the communication system for the JUICE mission. So Mattias, the word is yours.
Thanks, Michael. I was thinking, when did we work together? But that's already almost 10 years ago. So that means I'm getting old or older. Actually, I want to pick up on something that Dominique said about how I started in space, because I don't have a very romantic story. I just didn't know what to do, and But when I was 18, there was someone who came to the secondary school to speak about a university, a space university. And so it suddenly became an option. So I hope that we can do the same for you, that we can show you that that is actually an option. So let me go to my presentation. You should be able to see it now, right? Okay. Voilà. So I'm going to speak indeed about a mission to Jupiter, an ESA mission to Jupiter named JUICE. JUICE actually stands for the Jupiter Icy Moon Explorer. And specifically about the challenges of communication at such large distance. And I mentioned the 900 million kilometers because that's really the worst case distance that Jupiter will be from the moon. But I'm also going to give a rather large introduction, I think, about the mission itself, which I think is very interesting. We don't go to Jupiter every day. So it's interesting to show that young engineers like myself, and I hope I can still call myself an engineer, even though I'm more into project management, even after 5-6 years, we can work on such missions. So I want to give a bit of an overview of the science, the orbit, which I think is very interesting, and then from the spacecraft layout, I want to work towards our communication subsystem that we are actually building with Antwerp Space. I'm actually going to use quite a lot of material from ESA, so courtesy to them. One of this is, for example, all the mission that they've done to go towards outer planets. Proba is on here, Proba 2, which Stijn will definitely remember. But what you might also know is, for example, Rosetta, where there was a landing on a comet, which was well represented in the media. But actually, I want to talk about JUICE. So JUICE, that's the satellite. We're not there yet, of course. We are not going to launch until 2022. This is a nice image. So as Michael mentioned, this is one of the large class missions, as it's called at ESA, which in a sense means it's expensive. So there are a few of these missions, so one every few years. And this one is specifically for trying to understand the Jupiter system. And I'll explain later why that's very interesting. And as you can see there, it's mentioned what are the conditions for planet formation and the emergence of life. Now, clearly there is no life on Jupiter, but its moons represented quite interesting study object. So we plan to launch it in 2020, and it takes 7 years to get there. And then I will stay around in the system, the Jupiter system, for 3 years before it crash lands on one of the moons. And so we provide a communication subsystem. I'm going to sidestep to the academical competition, which is Juno. Juno is a NASA mission. It's looking quite different, the satellite, and it's already there. So it shows quite an interesting outlook on what kind of scientific results we can gain there. For example, you might have seen this specific image. Apparently Jupiter is blue, at least on the North Pole. So we all have these rather low resolution images of Jupiter in mind, but the resolution of the imaging that you can get these days by actually being there is quite amazing. And so Juno, even though again they're from the competition, they are making quite a good job there. So we are going to do this, but better. Unfortunately, only in 10 years from now, though. So why is Jupiter so interesting? It's first of all because it's gigantic. So it's factor 11 wider, so that means 300 times more heavy than Earth. And at the same time, it's rotating quite quickly. So this enormous mass with its velocity has it generates a large amount of energy. And that actually creates an interesting phenomena into its system. It's also orbited by I'm always surprised to read it. So 4 large moons, almost planet-sized moons, and then 60 smaller moons, as far as we know, which is apparently strange. We don't yet aren't entirely sure whether there could be more moons. And so in this way, it kind of resembles a mini star. If it would have been a bit larger, well, a bit, 80 times, but you know, that's relatively a bit, then it could have become a star on itself, and we would rather have had a duo star system instead of a single star system. And of course, I would not be having this presentation then. And due to the fact that it's so massive and so rotating so violently, it has enormous pressure inside, in seas, as it's, I find this on the NASA website, where they always are very good in wording it very interestingly. So Jupiter's powerful magnetic field could be generated by electrical currents in this giant swirling ocean of liquid metallic hydrogen. So you can imagine it's nothing lives there, but it's this energy that that is determining in a large extent not only its local, let's call it miniature solar system, but it's also having had an influence on the existing, on the formation of our solar system as a whole. So there's a lot of science there. I'm not going to go into detail. In the end, what is interesting is the magnetic and, for example, the magnetic fields that it generates due to all this swirling of metallic oceans inside, and the way that these react with the planets around it. And again, this looks very much like our own sun. It has a violent magnetic atmosphere, if you can call it that way, that interacts with our Earth. And measuring that magnetic field will also allow you to understand how the moons, or let's say it's miniature planets around Jupiter, how they are structured internally. And specifically for these icy moons, it's very interesting because we think all this energy from Jupiter will recreate tidal forces and hence also energy inside the planets, which could create the conditions of life, because of course they have water and heat. And so they're not going to be fish out there, but I mean, something more microbiological is definitely an option. Now, JUICE will not detect life. It will rather detect whether it's possible to have life. So this goes more on about, you know, how can you detect life? You can see certain chemical trace gases in the atmosphere. That's always a good one. You also want to see if there is heat inside the planet. So to heat the ice from below, create the possibility of internal oceans. The JUICE mission is quite long. It's because it's of course far, relatively at least. So it takes you 7.5 years to get there, and this is a list of how such orbits look, how to get there, but I think it's more interesting in a little movie. And so what you see is the white line is the spacecraft leaving Earth. Now it's going to make a nice flyby from Earth, and then it's going to inject itself via it's going all the way to Mars. I don't know if it's going to reach it. No, it's going to go to Earth again, and it's going to go a little bit higher to Mars, and that is going to give it its final kick. Oh, I'm lying. It's not giving its final kick. It's going to come back again, and it's going to do another flyby by Earth. There you go. And then we're going up, going all the way to the orbit of Jupiter, and the calculations have to be quite exact because all the way at the apogee is going to get captured by Jupiter. I kind of love this movie. And hoppa. Voilà, there you go. So quite an interesting calculation they made to achieve this. And of course, this is you want to use the energy of the planets to get there, because otherwise you need a massive rocket. So you can't get there in one go. So the satellite itself, that's the one. You might notice that it has different solar panel configuration as the beautiful image I showed earlier. And of course, that's design iterations that you do to come to an optimum configuration. Now, I'm not going to go into detail, apart from a few key numbers which are interesting. Actually, the solar panels that it has is 100 square meter of solar panels, which is, you need an enormous amount because actually this is fully powered by solar cells, the spacecraft. And you need so much because so far from the sun, you only have, it only generates at the end of its lifetime 850 watts, which is nothing. I mean, and on Earth, the amount of power that they would output would be tenfold or more. And the mass is no more than a big car, I think, so two ton. But of course, most of that is propellant. And a nice blown up image of that, what's in here. But what's interesting is, of course, most is the communication subsystem. So in order to communicate, you always need something which generates the signal, something which amplifies the signal, and something which broadcasts the signal. So you have always the transponder, you have the amplification chain, and then some antennas. On the JUICE spacecraft, it's quite complicated because you have two bands, X-band and K-band. K-band specifically for large data rates, and you have 4 antennas. And in order to connect them all together, maybe just a little factoid is that you know, you want to get the data from the spacecraft down back to the Earth, and you do this at certain speeds. You know, like you download from your home computer or iPhone, and you know, a simple home data link is easily 100 megabits per second. 100 megabits per second, and that's not too fancy. While what we are trying to broadcast at the so-called high data rate is only 1.4 mega symbols or megabits per second. So getting data down from Jupiter is not as easy as downloading the latest TikTok movie. So this all translates into quite a complex architecture, because not only the fact you need to connect all these parts up, but at the same time it needs to be single point failure tolerant. And what does it mean? It means that anything should be able to fail without the entire system failing. So that means that everything is redundant in order to be able to bypass a failed component. And apart from that, of course, it needs to survive such a long period in orbit, and funny enough, also on ground, because we built something in 2018. It's getting launched only by 2022, and then it needs to have survive another 10 years of mission. So in reality, that's how a communication subsystem looks like. I just took the spacecraft in a CAD model, and you remove everything that is the spacecraft, and this is what you keep. So it's an enormous, how do you say that, network of waveguides, cables, and units connected together. Quite the more visual aspect of that is what we call the RFDA. And just a set of, it's actually you could see it as the network that connects all the elements together. It contains all kinds of passive RF equipment, which I will not go into detail. But you can see this is only a central panel, while if I go back a bit, this is only the panel in the middle, and it needs to connect everything, so the reality becomes a lot more complex. And this is how it looks like in the flight configuration. Of course, a fashionable black and gold silver finish. This probably doesn't mean too much to the outsider. What you want to remember from this is that anything that you put on a spacecraft has to be at a very high quality, and it involves electronics, it involves mechanics, it involves any engineering aspect that you encounter in the daily life, in essence. So whatever your engineering studies are, you can work in the space industry, apart from maybe building, from civil engineering. Here you go, that's some key figures. The power consumption that this uses, again, I always find it very insightful, is only less than 215 watts, which means, I mean, just to compare it, if I heat up a lasagna in the microwave, I put it on 600 watts or 900 watts to get it warm. The power consumption is nothing. But of course, you need to remember that in Jupiter, we only have 800, 900 watts available. And the signal that you send back to the Earth is, depends of course on the wavelength, but you have in total 80 watts of RF signal. And this needs to travel all the way back to Earth, and we should be able to detect this. The main engineering challenges, let's say, is to be able to build something that does not disturb what we want to measure there. Because, as I said earlier, we would like to understand the magnetic and electromagnetic atmosphere around Jupiter. And so we have very sensitive equipment on board. And we cannot have our own communication subsystem completely blind those equipments with our own EMC signature. Other important constraints are the temperature. It should survive very low temperature operations, more than minus 30 degrees Celsius, not for the electronics, but for much of the passive elements. Also, typical things like shock, vibration. But what I find more interesting is what was mentioned before, also the severe radiation environment, because like our sun, Jupiter emits an enormous amount of radiation, which is caught in the magnetosphere and is constantly bombarding the spacecraft. This is why much of the electronics are actually in lead-lined vault inside the spacecraft in order to ensure that it survives at least, hopefully, 3 years in orbit around Jupiter. So all this complexity, in the end, it becomes, after several years of engineering and drawing and discussing and everything that comes with it, it becomes hardware. And this is what we ended up with the lab. It shows only a fraction. It shows, again, this panel. And then on the back, you see the amplifiers. And this is just like an easy integration in the lab where you have access. In the end, in the spacecraft, you're working in a clean room. You're working in essentially a bunker. And you have to fit this into the spacecraft. So what you see there on this picture is the spacecraft. It looks quite, you know, if you don't know what you're looking at, it looks a bit dull. It looks like a cube with some aluminum foil in it, but it's full of all this complex equipment. And you somehow have to fit your own equipment in there. So you actually have to physically get inside the spacecraft. And while on a CAD file, you can always orient your model like you want. In the spacecraft, you end up integrating it upside down. But at least this, even though you're always in a bunker, you get to work with this kind of, you get to build something which in the end will go to Jupiter. And okay, in this case, it will crash land on one of the planets. But often in the missions you work on, it will outlast all of us if it will remain eternally in an orbit around the planet. And what we build is likely to outlive the pyramids of Gizeh or any other what we think as ancient art that we build. So it's quite amazing to be able to work on these things. In the back is a satellite, by the way, in case you wondered. Well, that's our little team actually that we worked on. And this, the boxes contain the JUICE communication system before we send it. So voila, you see, actually, if you look at that team, that most of them actually were early 30s, in their early 30s. So you know, the opportunities are there. So I hope you can find your way into this industry and into the space world. Well, that's it. I don't know if there's time for questions. I probably doubt it.
Thank you, Mattias. You are perfectly on time. That's amazing. So thank you very much. I think we still have, if we count the schedule accurately, we have 2 minutes for a question. So I saw some question on the chat. maybe there is one nasty for you, Mattias, from Philippe, so from behind you. So, which I think is interesting because he's asking, okay, what about optical communication to increase data rate? So is Antwerp Space involved in optical communication? So I don't know if you can answer this question, or if you want me to say a few words, it's up to you. You are mute.
Yes, it's the usual mistake. Optical communication is always the interesting technology that has a lot of promise and that everybody wants to move to, but it's not that straightforward. What we are working on at this moment is rather to make optical components for RF communication. So not directly the full chain, but more within the subsystem or within the equipment to start with full optical components. And that's of course completely different than to have an actual optical link from a deep space mission all the way to the Earth. But the technology is promising, and we're trying to make our first steps inside this technology. I'm honestly not too much aware of all the ins and outs, but we are trying to move into that direction. So if you want to know more, I think we should have a chat afterwards.
No, but thank you, and thank you, Philippe, for the nasty question to Mattias. It's an interesting question, and it's to illustrate also the difficulties of the technologies that I was addressing. So, for example, for Earth observation mission, when Mattias was mentioning data rate in the order of 1 megabit per second, but when we go to Earth observation mission, where we come to huge data rate when we acquire so much data. So nowadays we slightly move to optical communication with the satellite EDRS, where there is an optical communication channel to download or at least to acquire some image coming from Earth observation satellite. So I think to stay on the schedule, I will go on with the next talk. So thank you, Mattias. So the next
If I could just add one small thing, actually, as you mentioned high data rates, we're actually in the process of developing a very high data rate transponder at Antwerp Space, and it's still meant for deep space, but we're actually looking for much improved data rates. And this project will last for a couple of years, but we hope to end up actually with a transponder of our own that we can compete with on the market for deep space transponders. So that's an interesting development that we're doing on our side.
So the next talk will be completely different. We will go to the moon with Stijn. So Stijn, I had also the pleasure to work with him many years ago. So Stijn is what we call was working as an IT engineer, so responsible for the assembly and testing on the spacecraft. He did it on a past Belgian mission. I get to know him on Probavi, on the vegetation mission from the Belgian satellite. And now he's still working on the Belgian Proba mission as a project manager. He wrote a book, and this I didn't know. So Stijn, congratulations! I would be very curious to read it. So Stijn will talk about the moon, and as I said in the introduction, so talking about the technology needed to go back and what is already existing and what is needed to be developed. So thank you, Stijn.
Okay, good afternoon, good evening, everybody. Can everybody hear me and see my screen? Okay, all fine. Just there was some romance talk in the beginning, and I realized that working in a Eurospace Center for a couple of years looks like it's romantic, but actually I met my wife there, so it was actually very romantic. So you can meet also your wife by doing your passion working in space. Just to see whether I can move along the presentation. I wanted to start the talk not by explaining that I work at QinetiQ. I will mention the brand QinetiQ a couple of times. But I wanted to explain a bit what my personal story was, and I wanted to start with the story of Gunther Wendt. I don't know whether anybody of you know who is Gunther Wendt. It's the guy in the back of the picture. It's not the cool guy with the helmet which is going to the moon. It's actually the guy who's preparing everything such that this nice little astronaut doesn't die on its way there. Gunther Wendt was the guy who closed the hatch when the Apollo lifted off. And I always wanted to be part of such a big mission. I wanted to be Gunther Wendt, to be my little brick in the wall of supporting such a big mission. And actually currently, okay, at QinetiQ, but also at other companies within Belgium, we are contributing to the new race to the moon. And I'll try to give you a bit of an overview. In my personal career, I didn't get to go to the moon yet. I was not in Houston, but I was in ero-G, which is a very small village in Belgium. We launched there Proba 1, Proba 2, and Proba V. I was the driver, the operator at the screen of Proba 2 and Proba V. We went to ESOC. So even if you work in Belgium, it doesn't mean you're only working on Belgian missions. You're working on JUICE, like Mattias said. I was working on an interplanetary mission to deflect an asteroid from hitting the Earth. We were not in the Kennedy Space Center, but we were in the Centre Spatial de Guyane, which is also fine. The climate is a bit different, but it's a lot of fun as well. But in the background, you see the Proba V satellite in 2013, on which Michael was also working. I didn't do any Saturn V, but I saw 2 Ariane 5 launches, and we launched also something on a Russian former nuclear rocket and on a Vega rocket. So I get to see in my, still young as well, I'm 40, so I still count myself as a young engineer, but I saw my share of rockets, and that's in the end what we do it for. If you want to work in space, you have to find this cool, because otherwise space is just boring and it takes a very long time and everything needs to be exactly right. But as long as you have the dream of working in space, then all that doesn't matter. So you just enjoy being a part of these big projects. We got to hug a rocket. The one on your left is the Vega rocket. And indeed, if you work in space, I remember a time when I was working on the Herschel Space Telescope, and I got to write my name on the satellite itself, a small thing of aluminium foil. So my name is now somewhere 2 million kilometers away from Earth, and it will remain there forever and ever until some kind of UFO finds it and then thinks, oh, Stijn Ilsen, who's that? He's written a book. You see the team on the right. But that's more about my story. I just wanted to make sure that you understand that even if you work, because space is very European, very worldwide, but even if you work in Belgium in space, that doesn't mean you work only on small little things. You can really be part of very big missions, whether they're Belgian missions, European missions, or even missions of NASA. You're really not in a corner. Belgium is really one of the key member states of Europe contributing to space. That's very important. Going back to the moon, I can't find any cool picture of an astronaut on the moon, which is a bit recent because we haven't been there for 50 years. But this is one from Mars, but it's the same message. This guy, if we want to send humans to the moon, he needs water. He needs to exercise itself because the gravity is not there or is only partially there. He wants to be brought there in a safe way, and for sure he wants to get back home. Of course, he needs also food. And sometimes he might want to be interested in getting some pictures from home. And in all those aspects, QinetiQ has projects. So we are very broad. We are using scientists, engineers, and many people from many different origins to bring the knowledge together to do this. If we start with water, then you can imagine a call from some prince or a king calling to an astronaut on the moon saying, oh, how much water do you need? And the astronaut will say, I'll need about 4,500 liters of water per year. The king will be not really amused because just counting the launch costs, this will cost about 1.6 billion euros just to get the water for one astronaut for 1 year on the moon, which is just something we will not be able to pay. But then the astronaut will say, don't worry, we have QinetiQ Space. They've built a water treatment recycling machine, and they're actually recycling my, well, you know, the wastewater of astronauts. And this is a bit how it looks like. We are building something from for the ISS, International Space Station. We have a similar system deployed on the South Pole, which you see on the top in the Princess Elizabeth base, if I remember well. So within QinetiQ, we're not just building satellites and stuff like that, but we're also trying to find ways of applying water science and therefore eliminating this cost of sending water to the moon by just being able to recycle in situ. The guys also need training. I've brought a nice movie. It's already 10 years old, but we have done this more often. But at some point in time, the treadmill of NASA was found to be not very user-friendly. The astronauts didn't really like to run on the NASA and the Russian treadmill, but they do need to exercise. So the question came from ESA, whether we could develop a treadmill which runs more natural, with a force damping system, which would keep the astronaut in a more flexible way, compressed to the treadmill. And if you build that kind of hardware, you need to be able to test it. And the only way you can test it in zero-G is either in space, in a drop tower, but the drop tower is only for a couple of seconds, or you go to in a plane. If you see in the background, there's Frank de Winne, or Belgian astronaut. So if you work on these kind of projects, you get to go in the Vomit Comet, which is the name of the plane. You get to be sick all the way from the beginning to the end, but also enjoy that astronauts are running on your treadmill, and you learn a lot by their user experience. Another system which we are currently developing is really required if you want to go back to the moon, because we will not be able to fly there with a single spacecraft. We will have to dock in space. And in the past, there was a Russian docking system, there was a European docking system, there was an American docking system. There were all kinds of different tastes and flavors, usually male, female, and those don't fit on one another. So it creates a lot of complexity to be able to get these people to the moon, because you need to have the right docking rings available. In the last couple of years, a standard called IBDM has been established, which would provide a single docking system which fits on all of the ports. And QinetiQ Space in Belgium is very proud actually to be able to develop the European version of that docking system. We call it one docking rail to rule them all. We'd like to be, we're engineers, we're never really cool, but we try to be cool by just adding some lines under our product names. Where do you actually go? We go to the gateway around the moon. As you probably heard, the ISS around Earth will get a small little brother, which is a space station around the moon. And the space station around the moon will be used to fly to and then fly in a descent module and then go to the moon and come back. So this gateway is actually currently under contract for many companies within the US and Europe and other contributing nations. And we're part of that. We will build the docking systems for the two European modules, which is called the IHAP and the Esprit. And we're actually very proud of that. Currently, we're building this system, so we can show you a small little movie on how it looks like. You would think docking is rather straightforward. You fly to each other, you bump into each other, and then you take some hatch, you close it, or some hooks. But in fact, this is a very tricky aspect of the mission, because you fly two very heavy spacecrafts with a certain relative velocity toward each other, and you need to be able to dock in nearly all possible conditions. Whether you fly straight, whether you fly a bit too fast, a bit under an angle, and you all need to test this. And there we're actually extremely proud that from the different systems, which are also available from SpaceX and from Boeing, the Belgian system, which is built in Kruijbeek and in Antwerp, is actually the one with the most successful docking chance. So even if you fly a little bit left or right, you still have the best chance of actually docking with your system, which eventually is the only thing which really matters. If you want to dock with humans on board, you will have to have a very big chance of success. Otherwise, this will just be very tricky. This system is fully safe in that sense that we are able to even dock if we have an issue with our electronics. Of course, it might be a bit more bumpy, but we will be able to dock, which is the most important one. We don't just build structural things. We don't just build electronics, motors, but you also have, for example, model guys. We need very brilliant engineers who model these things, such that you can reproduce the test in your model, and you can therefore also reproduce, or you can use this model then to see what kind of behavior your system would have in other systems, which you just cannot test on the ground. And that's very nice to be able to do that. To get back to home, you might also want to use an ion thruster. It's probably not to get back from the moon, because the ion thruster is a very low power thruster, but it's basically used to fly to Mercury, to Jupiter, these kind of things. And our UK colleagues from QinetiQ are building these ion thrusters, which are a bit futuristic, but actually they work very well. A nice little project within QinetiQ as well has to do with spirulina. It's part of the Melissa project. Spirulina is a bacteria which you can buy in any kind of healthy food stores. My wife has bought spirulina at some point, and I probably have eaten it as well. It doesn't taste very, very nice. I understood it's also used to get the blue color on the M&Ms, but that's not really what I wanted to explain you. Spirulina is a bacteria, and if you give it CO2, so what the astronauts exhale, and if you give also some N2 and you then shine light on it, then the bacteria grows while producing oxygen. So it's really your perfect recycling machine. You take your dirty air and your waste, you give it to this bacteria, you just shine some light on it, and it will provide you oxygen, and it will provide you food. I don't think the astronauts will be happy of having to eat spirulina all day long, but still, it's very nutritious. So in the end, it will be able to sustain the astronauts there. So there are some experiments currently running on the International Space Station, and QinetiQ has built one of these experiments. So what you see on the left is actually some kind of container where different samples of this spirulina bacteria are included, and we are then shining light on them to see how they grow. And this was just the first experiment, but the results are very promising. Now we need to make it bigger, because we could not really harvest any spirulina. It was just to see how they grow in space in zero-G, but the results are very promising. And if you work on this project, then you get to go to SpaceX, because this flew on a Dragon capsule. So these 4 colleagues were very lucky and went to SpaceX for some weeks. And then the astronauts might want to look back at the Earth, at the blue planet which they came from and which they want to return to, and to take images of the Earth. The best way to do that is by going to space. And we already launched from QinetiQ 3 Belgian satellites. First one in 2001 was Proba 1, then Proba 2 in 2009, which is looking at the sun more than towards the Earth. And then 2013 was also a vegetation mission. The nice thing about these satellites is, even though, for example, Proba 1 is now 19 years old, and it was actually built to last about a year to maybe 1 + 1 year, so maybe 2 years. I was not there at the time, but I have some colleagues who were there, and I think if I asked them, they would be very happy if the spacecraft would just have survived for 3, 4, 5 months. But even after 19 years, the satellite is fully functional, and it's operated from Rutger every day, and it still makes its daily pictures of the Earth. Same for Proba 2, built for 2 years, still operational, and also Proba V, still operational. So actually, we're building our hardware a bit too good, because our customer doesn't want to buy new satellites because the old ones are still working. So maybe we should have some kind of trigger in there that they fail on command in some way. We have lots of upcoming satellites. We have Proba 3, which is a satellite which will fly information with another satellite. It's probably difficult to see, but you see 2 satellites in the picture on the left bottom corner, and one satellite has a round disk, and it will fly in front of another satellite such that it will create a shadow cone, and this shadow cone will create what we call a solar eclipse onto a detector, and then the detector will be able to see the corona of the sun in an unprecedented way, something you cannot see from the Earth, nor from other spacecrafts in orbit, because the spacecraft are about 150 meters apart. A very, very complex project. We're working on that very hard, currently in a test phase, but very, very nice to work on. Altius, which is a new Belgian satellite looking at the limb of the atmosphere, so looking at gases in the atmosphere, therefore looking at ozone, looking at CO2, looking at really important gases to help support climate studies. And then we have another setup which is called HERA, and HERA is a very nice mission because it will help humanity at some point in the future, because it will rehearse a mission to deflect an asteroid which is aiming for the Earth. It's a very nice mission which will at some point maybe become in handy if we ever find an asteroid which goes directly to Earth. That's basically the end of my talk. I hope I could inspire you a little bit and try to see the enormous range of engineers and people we need to get these projects launched. It's not just about one mission analysis guy who calculates trajectories. No, it's more about structure. It's about thermal. It's about electronics. It's about project managers. It's about test engineers. We need optical engineers. We have a lot of vacancies currently within QinetiQ. For my personal project, I'm looking for at least 12 people in the next couple of months, and it's really holding me back. So if you have any ambition in working in space, any kind of experience, any kind of things you learned in school which can become handy, have a look at our website, and then we might be able to see each other in some kind of interview in the future. Thank you very much.
Thank you, Stijn. I cannot see a question on the chat, so that means that your presentation was super clear. So anyway, we are, I think, 5 minutes a bit out of schedule, but the only thing I wanted to use one of your words to introduce the next speaker, because you mentioned that for space you need to be patient, and this is, I think, very important to say, because indeed it takes time to develop a space mission, a very long time. I don't know, Stijn, you didn't say it, how long it has taken QinetiQ to develop IBDM, so this nice docking system that you have seen, but it is a lot of years. So it is not something that you do it quickly. So you need to be patient indeed if you work in the space sector, because it takes really a certain time, because you want to be sure that it works. So this is before you launch it. So and this is the introduction to Rutger, who is working at OIP, which is mainly an optomechanical industry in Belgium, in Oudenaarde. And Rutger is, as I said in the beginning, will show you just the phasing of the development of a mission, and then you will understand a little bit why it takes so long, because it is very long between the idea up to the launch. So I leave you the word, Rutger.
Thanks a lot, Michael. I'll try to share my screen from home. I'm gonna try to go to presentation mode. Can you see the screen, or can you see my one with the notes?
We see with the notes, Rutger.
Yeah, that's a bit unfortunate. Yeah, you would think the one good thing about the Corona crisis is that you get good at Zoom meetings, but unfortunately, yeah, I can only share a window. Apparently, it's not giving me the option to share the full screen. All right, we'll have to do it like this then, I believe.
Yes, if you don't have any animation, that's fine, Rutger.
I'll decouple my second screen, makes it a bit easier then. All right, so thanks for the introduction. Today I'll be giving a bit more broad talk, let's say. Unfortunately, I could not be there due to other obligations which prohibit me to travel to Brussels on time. So I'll unfortunately not be able to talk to you all in person and enjoy the very lovely caterer, which I'm told is one of the best in Belgium. But if you have any questions, indeed, feel free to ask them here online or after the session. Feel free to pose. So the idea of the talk for today is to discuss a little bit the ins and outs of the design, development, and verification of electro-optical payloads, being one of the key expertises at OIP Sensor Systems in Oudenaarde. Despite what the title says, I'll not be going through the entire alphabet today, mainly due to time constraints. So we'll actually be stopping after about 5 or 6 letters into the alphabet. And the idea is that we basically walk through the various phases of an European space project, so a standard ESA space project. We walk through the various phases, and I will present some key aspects, key criticalities of those various phases, as well as some specific technologies in the various design phases. So actually, I'll not be going through all of the phases, but mainly the ones where we have a heavy involvement, also from industry sides. So every mission obviously starts with an idea. This is the phase 0, where a mission is actually analyzed based upon the needs of the mission, and the initial user requirements are put forward. This is really something that happens at user sites. It's the user together with the agency, obviously, deciding on what do we want to do. Only in the next phase does industry get more heavily involved, and do we start presenting and evaluating the actual feasibility. Can it actually be done? So those are the phases A through E, where industry is quite heavily involved. The final phase is the F phase, where the mission is then finally disposed. Some missions last forever, as was already said by previous speakers, but quite a lot, for example, for Earth observation, need to be properly disposed and deorbited, and basically burn up in the atmosphere. So going out with a bang quite. Okay, so bringing us first to the phase A. As I said, the phase 0 is more the user deciding on what do we want to do with the mission. And the phase A, it will be involving industry as well to try to identify, can it actually be done? And as I say here in the subtitle, anything's possible with sufficient budgets. That's very much the truth, but budgets can be more than just monetary budgets. Of course, throwing more money at something can help making it become a reality, but it also has to be feasible within the technical budgets. We're talking about things like power, volume, mass budgets also have to fit, obviously, with the mission constraints. So that's what happens in a phase A. Industry will start looking at potential mission concepts, potential system architecture to fit with the requirements of the user, to fit with the mission needs. Based upon those possible concepts, those are traded off against one another. And the goal of this phase is really to come forward with a final answer. Is this mission feasible, yes or no? Again, within the budgets. So for example, on the left-hand side, you see an early concept for one of our spectral imagers. It's an optical concept, which is very much simplified. All of the optics are simplified basically by means of a lens in the beginning of the instrument and a lens at the end of the instrument. And then you have a spectral filter in the middle, which can basically be tuned and select a given wavelength to pass through the instrument. So these kind of things are really identified and elaborated in these early phases of the project. What's also looked at during these early phases is that oftentimes you identify key technologies that will be required to successfully complete this mission or elaborate on the mission. And often the agency, as Michael already said, the agency does not always like new technology being used. It's more about reliability and if it works, never change a winning team. But sometimes you can do nothing else than use new technology. And in these cases, it's often beneficial to elaborate on these new technologies and to propose certain pre-development activities to dive into these technologies and prove that they can work in a space environment. So at the end of the phase A, we have the preliminary requirements review, which basically can give an answer to the question, is this mission possible? Yes. So then we move on to the phase B. If we have a successful PRR, we move on to the phase B, where it's really the messages to the drawing board. So the phase A concluded that the mission is possible. A project can be made to the user requirements. Then in the phase B, it's really a matter of doing it, starting the design on all levels, optics, mechanics, electronics, and making it all fit together in the end, and proving that you can sustain the space environment and meet the mission requirements. So that's when we really come up with the preliminary design for this concept that was selected in the phase A, and starts detailing that's up to the PDR level. On the right-hand sides of the screen, you see, for example, the pilot camera, which is a camera developed also by OIP to be used on lunar descents. So basically a very broad field of view camera, about 70 degrees, if I'm not mistaken, which is used during automated descents on lunar landers. And you can see the Flex Rigids PCB, which contains all of the electronics, readout electronics for this camera, being fit into what is a very constrained volume envelope. So you have to twist and turn the electronics to make it fit. These are the kind of things that are investigated in the preliminary design. Of course, you also have to prove that this design, it will work. So you have to do quite a lot of analysis as well to prove exactly that. In the bottom of the screen, you can see the outcome of a stray light analysis. This is the point source transmittance for one of our instruments. So the stray light analysis, it's basically a ray tracing analysis where you take several millions of light rays and you trace them as they traverse through your instruments or through your optical units and until they finally fall on your detector. And you can basically simulate what your detector, what your instrument will be seeing once it is in orbit. Part of that is the light that you want to fall on the detector, and part of that is just light, stray light, as we call it, that you actually want to avoid falling on your detector. And then you could take design measures to reduce this amount of stray light. So also in the phase B, you'll be looking a bit more into the programmatic side of things. On the industry, it will be up to industry to propose a certain verification approach and a certain model philosophy for the mission. That can be, okay, we have a lot of new technologies, so maybe we need to build a qualification model to really prove fully that that system will work before we go to the flights, or maybe not, and we can go to a flight approach. Those are the kind of things also being decided upon in the early phases, in the early phase B. Of course, as a system integrator, as we are in OIP, you have to acknowledge at one point that you're not the expert authority in every single technology. So a very crucial aspect to system integration is knowing the industry and knowing where the experts are located. And that's actually then also in this phase B that you will start putting together your industrial consortium, start looking towards European partners, but also worldwide partners for key expertise in the development of subunits of your instruments that you want to build in the end. Of course, all of this is related to a certain schedule and costs, depending on the criticality and depending on the maturity of the developments already. This can have an impact on schedule and cost. So also all of that needs to be consolidated somewhat in the phase B. The end of the phase B, we have a very important milestone called the preliminary design review, or PDR, where you present your design towards the customer, and it is evaluated if this is worthwhile to go ahead and to really start going into the more MAIT heavy phases of the project. We actually have, for one of our projects, the Altius instrument, we have the PDR currently ongoing. And I think, Mikael, you're part of the review board for that one, for which you have collocation tomorrow. So I'd like to take the opportunity to ask you not to be too hard on us tomorrow, if you can. So that's the PDR, and that concludes on the phase B, after which we can move towards the phase C, which is really the detailed design phase of the activities. So there, okay, we concluded at PDR level that we have a design which is worthwhile to detail, and which is proven that's by analysis mostly, but it's proven that it can meet the mission requirements and can survive in a space environment. While in a phase C, you take all of that and you detail it even down to the lowest level, so really down to the smallest bolts and the smallest resistor. You'll be detailing all of that in the phase C. Of course, you need to prove with further analysis. The more you detail, the more you have to analyze. So you need to prove also, keep proving that also with all of these details, the design still holds true through the mission requirements. So as an example, in the top of the screen, you can see the finite element model for one of our instruments, actually the Altus instrument, which contains approximately, if I'm not mistaken, 1.5 million nodes in the finite element model. So these are really individual nodes all connected to one another to model basically the structural behavior of the instrument. So you can start simulating what the instrument will behave like under vibration loads, what will be the eigenfrequency, which are aspects we still need to stiffen a little bit the structure. Things like that are really all investigated also still in the phase B also, but definitely in the phase C in detail. You also see on the left side of the screen, yeah, analysis is good and well, but still the proof of the pudding is in the tasting. Fortunately, there we go. So in the end, yeah, okay, what you also do in a phase C, you have all these key technology, key units, which you will be developing, prove them that they work. So you start building qualification models of these units and start basically simulating the space environments upon them. So you take them through thermal vacuum testing, take them through shock testing, vibration testing. And actually over here on the left-hand side, you see the vibration test of a qualification model of a tunable filter, an acousto-optic tunable filter, which is a technology used in the Altius instrument, one of the 3 channels of the Altius instrument, as it is being vibrated. So with quite a lot of margin, you simulate the space environments or the environments during launch on this unit, and you can basically prove by tests that the unit will survive the space environment. We do those qualification models in the phase C mainly on unit level, not so much on system level or on instrument level, which is more of an activity for the phase D. What we do on instrument level in this phase C is look more towards engineering models, such as an electrical model or a structural thermal model of the instruments, which each have then their own limited representativity, but the representativity that they need for the electronics engineers to start debugging, or for the structural engineers to correlate to the finite element models and see that the analysis were right in the end. They often aren't, spoiler, but that's why you do these kind of things, to correlate and really come to a nicely correlated model in the end. So in the end of the phase C, we have another review called the critical design review, which is really can be considered the go-ahead or the starting point to start with the actual QM and or flights activities in the phase D then. So we've seen a couple of phases now already. I often also ask during interviews with new people at OIP, I often ask, what is your favorite phase of a space project? Because it tells me quite a lot about their personality, in my opinion. You have the phase A people who are really theoretical and like to have a lot of broad landscape to work in and try to find potential theoretical solutions that fit. You have the phase C people who are often okay, the so-called nitpickers. It's not an insult, but for sure not. You need those kind of people, but who really like the kind of detail of typical to the phase C activities. The phase D people are really the people that like to get their hands on hardware. It's really nice. You need a space sector. It's an inspirational sector, as Stijn already said. So it's really nice the first time you get to touch a bit of space hardware yourself. So that all happens mainly in the phase D, where you'll be doing the detailed the qualification testing if you have indeed a full QM of your system and all of the associated verification activities, which then leads to the qualification review, where you basically have proved full on non-stop your system will survive space environments with quite a lot of margin. That basically gives the go-ahead to then start with the MAIT, so that's manufacturing, assembly, integration and testing of the actual flight hardware and software, which is then finally concluded by an acceptance review, where basically the users okay, it is ready to be flown at that point. So also here two examples from rather recent OIP developments. The bottom left, you can see the ProbaV instruments already discussed in Stijn's presentation as well. So that was used or is still being used to monitor vegetation on the Earth. It's actually composed of 3 spectral imagers, each covering their own field of view, and each able to monitor in 4 wavelength bands the various types of vegetation on the ground. On the right-hand side, you have a small part of the PROBA-3 mission, which is the focal plane assembly being developed at OIP. So that's actually the detector and all of its surrounding housings, mechanical housings and electronics around it. But for that one, we actually have very, very stringent requirements on the positioning of the detector. So we need to be able to position that detector with an accuracy of a few tenths of microns, so micrometers, which is really, really stringent. So you can actually see the detector and the focal plane assembly being integrated here and being aligned on the detector alignment station, where we use a combination of LVDT probes and actually a microscope where we can look down to the detector, the pixel level on the detector, to align this detector within the accuracies of tens of microns, basically, at that point. It's also a very interesting development.
So, Rutger, you have to conclude.
To the phase E1.
If we want to keep the schedule, so.
Yeah, sorry, it's my final slide. I'll quickly go through it. So that's the phase E1, then the final one where industry is heavily involved. I call it a bittersweet goodbye because, okay, it's a culmination of all of your work, years of work. So it's nice to see it all coming together and being put into a launcher and being finally launched. But still, it's also the last time, once the fairing closes, the last time that you see your product where you have been working on 3, 5, or maybe even 10 years of your life. Very much a bittersweet goodbye. So that's basically after it is then launched and the early commissioning is performed and the calibration in orbit is performed, that's where the involvement of industry really ends and it's handed over to the users for the operations. So that's it for my presentation. If you have any questions, feel free to ask. There's a bunch of links here to our LinkedIn pages, our websites, same as our partners at QinetiQ. We're also looking for quite a lot of people these days. I think we have 11 open vacancies at the moment, electronics, mechanics, but also project control, things like that. So feel free to have a look if you have some questions. Thanks a lot.
So thank you. Thank you, Rutger. So you were a bit longer than the others. You had less slide than the others. So thank you for your presentation. So I will move then directly to the next presentation from Philippe. So Philippe introduced himself already a little bit during the introduction. So he has a long career in space, starting from the public sector, even at the ESA. Or at CNES in Kourou, and then moving to the private sector in Air Liquide or Alstom. So now he's managing an important company in Liège, AMOS, in charge of optical development. So I leave you the word, Philippe. So you will give us a broad, let's say, introduction of optical instrument for ground, but also space for science and Earth observation. So I leave you the words.
Thank you. Let me share my screen. Okay, so I hope everybody can hear me. Indeed, so I'm going to take a much broader perspective in my presentation, and I will have to go very fast because it's so broad that in 15 minutes it's a challenge to cover all of this. I'm going to just show you how state-of-the-art instruments help us to understand better the universe and to protect our planet. So let's go very fast. I already introduced myself, so I'm not going to repeat what I said earlier. It's just, ironically, I started my career in Liège. I moved in different countries, Netherlands, French Guiana, France, and then now I'm back in my home country in Liège, heading AMOS now since 5 years. So all the projects I'm going to show you today are actually projects where AMOS is involved, with only 2 exceptions, which I will mention. So how do optical instruments help us to understand our universe? It's a huge question, and I'm going to try to highlight two main questions in 1 minute. The universe has a history, as you probably know. It started 14 billion years ago with the Big Bang. And when you look at how the universe evolved from the Big Bang to today's structure, the very homogeneous gas collapsed in galaxies and clusters of galaxies. But there is a big mystery because we don't understand why it collapsed so fast. And one of the answers that scientists give us is that there is probably a lot of mass, more or in addition to what we can see with optical instruments, which is so-called the dark matter. Actually, we believe that about 80% of the mass of the universe is dark matter, and only 1/5 of the matter is ordinary matter. You have a second confirmation when you look at galaxies, and when galaxies are rotating, you would expect that the stars at the center would rotate faster than the stars at the periphery, like planets in the solar system, but this is not what we see. We see galaxies rotating almost like a solid disk. And again, the only explanation we can have is dark matter. So we are trying to understand this, but for the moment, nobody knows what it is, and it's not possible to detect it. The second big mystery of the universe is that, of course, you all know the Big Bang story. So this big expansion at the beginning, and then suddenly the things are supposed to slow down because galaxies are pulling towards each other due to gravity. So you would expect this slowdown to continue forever, but this is not what we are observing. What we are observing is that since 5 billion years now, we see that the universe is accelerating. The expansion is not slowing down, and nobody understands why. So the scientists don't like to say, I don't understand, so they give it a name and they say, we've discovered dark energy. Actually, that means we don't have a clue, okay? And so when you make the estimation, you realize that this dark energy is about 3/4 of the content of the universe. So if you add dark matter and dark energy, this is 95% of the content of the universe that we don't understand. So this is why we keep doing telescopes and space missions. We need to understand what's going on there. So very classical instruments that you've probably seen already are ground-based telescopes. And this picture is showing you the biggest astrophysics observatory of Europe. It's based in Chile, but it's done by Europe. It's composed of 8 telescopes, 4 big ones. The big ones in the back are 8 meters in diameter, and 4 small ones called the auxiliary telescopes, 1.8 meter in diameter. The 4 small ones have been done in Liège, in AMOS. So now the trick with this, this observatory is that there is a very clever way of operating it. Instead of just looking in each telescope individually, what the astronomers are doing is that they are combining the light of the 8 telescopes through tunnels underground. The light is collected to one single point. There it interferes. And with very clever algorithm, you can recompose a picture with an incredible accuracy, the same accuracy as if your telescope was 200 meters in diameter. So that's a very clever trick called interferometry. And so let me show you what this telescope or this observatory is able to show now. So this little video shows you stars 25,000 light years away at the center of our own galaxy. And so you see those stars are moving. And they are moving around a point which is symbolized by this cross here, but there is nothing to see in this place. So they are orbiting about an object very massive but invisible. So there you have the first proof of the existence of a black hole. So this is the black hole called Sagittarius A star at the center of our galaxy. So this type of telescopes are now called classical telescopes, and this is the type of products we do in AMOS. So the picture you see on the left is a telescope which is in our workshop right now. It's about finished. It's going to be sent to India in about a month's time, 2.5 meters in diameter, and it gives pictures like the one you see on the right with a huge amount of galaxies in the sky. I want to introduce a few technologies that we use in these telescopes. This is not only about polishing mirrors and having stiff structures. It's more complex than this. A mirror that you see there at the bottom, it's 2.5 meter in diameter. It has been polished. It takes 18 months, 1/8, so 1.5 years to polish a mirror like this in our workshop. So you better be careful when you have your screwdriver in the hand, not to drop it there, because it's you have to start again from scratch. This without a pen. Now, the mirror you see there is not the Mount Abu mirror, because this is past generation. This was a very stiff, very thick mirror, very heavy, that required very stiff and heavy structures, costly. What we do now is we use very thin mirrors, and in order to keep the perfect optical shape, to keep the best quality of the image, what we do is we do active control of the shape of the mirror. How do we do that? We have hundreds of sensors measuring the shape all the time. When the wind is blowing, when the temperature is changing, when the telescope is rotating, we are correcting all the time the shape of the mirror with hundreds of actuators. So this is called active optics. The frequency of correction is about 2 or 3 times per second. So you see already that this is no longer a classical optomechanical system. It becomes much more sophisticated. And I'm going to speak about further technologies in a moment. But here, another example, this is on the top left, you see the back side of a support of a mirror of 4-meter diameter for the biggest solar telescope in the world. So this is in Hawaii. And what you can see here, I will show you on the bottom right, it's a small video of the surface of the sun. So what you see here is the convection of the hot gas or the plasma that is 6,000 degrees at the surface of the sun. Every one of these cells is about the size of France. So you see the kind of progress, scientific progress we can do with this type of active optics system. Now let's move to the next generation. So what I showed so far is in existence, it's working, it's proven, but now we are moving to new steps. And the next step is to increase the size of the telescope about 4 times in diameter. So the next generation telescope that you see there is 39-meter in diameter for the primary mirror. It's called the European Extremely Large Telescope. You understand why. And you see there on the bottom of the picture, you see cars parked in front of the telescope. So they give you the scale of that thing. It's really huge. So there is no way you can build a 39-meter diameter mirror in one block. What you need to do is take small pieces, small mirrors, and put them next to each other in order to rebuild a perfect shape. So every one of these 980 segmented mirrors have to fit within a few nanometers to each other. So, and this is also controlled real time in active optics, because you want to correct the effect of temperature change, movement of the telescope, wind blowing. So you see there, the challenge in terms of technology is huge. So AMOS is doing the system engineering study for the structure of this telescope. For sure, we are a small company, 110 people. We cannot build a telescope of that size. It's just too big, too expensive, but we are playing a very important engineering role in this. Now I'm going to introduce another key technology in this, because when you look at the sky at night, you see with your naked eyes that the stars are blinking, right? Everybody's seen that. They are not stable because there is turbulence in the atmosphere. And so when you make a long picture of the sky with turbulence, what you see is what you see there on the left of that picture, which is bottom right. Okay, you see a blurred image because the turbulence is blurring your image. Now, what we do with this kind of big telescopes is adaptive optics. That means that within the telescope, we have flexible mirrors, deformable mirrors, that we are using to correct the effect of the turbulence in real time. 1,000 times per second, we deform this mirror to do the exact opposite perturbation than the atmosphere is doing, so that at the end, you see the picture on the far right on my picture. 2 stars, whereas you could only see something very blurred originally. So this is called adaptive optics, and we are, for the moment, developing this technology for smaller telescopes. This is, for the moment, only used for very large telescopes, but we are trying to democratize that for smaller size telescopes. Now, let's talk about something. This is one of the two projects where AMOS is not involved, but it's so extraordinary I have to talk about it, the Event Horizon Telescope. I think everybody has seen the picture of this black hole last year. Amazing. This black hole is so far, you would never dream of seeing it. So what they are doing there is reuse the interferometry principle that I was mentioning before. This was 200 meters base. Here, they are using thousands of kilometers base by using several observatories on different continents. So there are radio telescopes here. So with this radio telescope, you are able by calculation to recombine the signals received by each one of those observatories and have this tremendous resolution of the picture that can show you the single black hole there in the center of another galaxy, which is, I don't remember how many million light years away. And so what you saw last year is probably a still picture. Since then, they kept working and they are now able to model and understand the dynamics of this black hole. So this little video shows you what we believe is the dynamics in about half a year. So very, very impressive results. So that's not the end of the story, because everything I showed so far is using light as the medium for bringing information from the universe to us. And that was, until 5 years ago, the only way to know what's going on in space. Now we have a new window opening. This new window is gravitational waves. Einstein predicted that space and time would be distorted by mass, and violent events where very massive objects are interacting can create waves in the fabric of space and time. And this is exactly what we can now observe using gravitational waves detectors. There are 2 in operations right now, one in Europe, one in the United States, and there are more in preparation. So I just want to let you know that there is a big project called Einstein Telescope in preparation right now. The project is to build this near the Belgian, Netherlands, Germany border. So the first contracts are being placed right now. The Centre Spatial de Liège is working on it. AMOS is working on it. The only way you can detect those tiny fluctuations in the fabric of space and time is through measurements, incredibly accurate measurements. So the only way to do that is to have a long basis. So you need 10 kilometers basis for your instrument, and making interference between rays of lights, you can detect 10 to minus 18 relative motion so relative distortion of the distance. This is the type of accuracy you need. Actually, I think I will make a little parenthesis here. This is probably the only mistake that I heard from Einstein. Einstein predicted that those waves could never be detected. He thought this was technologically not feasible. He was proven wrong 5 years ago by the Virgo and LIGO instruments. The next step will be in preparation within the European Space Agency, is to do an even bigger detector in space, because Earth is too small. So the idea is to have 3 satellites doing this kind of triangle 5 million kilometers away from each other, so we could have extremely sensitive measurements of gravitational waves in the future. We are not in AMOS involved in that project. So let's come back now to more short-term and traditional projects. There is one reason why we need still to go to space for astronomy. I've showed you that active and adaptive optics gives you extremely good results in terms of observation. One reason you still have to go to space is because the atmosphere is not transparent in every wavelength. In infrared, in X-rays, for example, you have to go in space if you want to see what's going on. So this is an example of a space telescope being built by ESA right now, called Euclid. The mission of that space telescope is to understand better the acceleration of the universe, to try to understand the dark energy I was explaining earlier. So you see that today we have measurements with large error bars. This is the expansion rate of the universe, and we need to get much more accurate in order to understand what's going on. So in AMOS, we are doing optics, and we are polishing and building extremely accurate mirrors for this type of mission. I will give more details in 1 minute. Okay, so now I'm going to turn our optical instruments away from the space, and we will turn them to the bottom, towards us, towards the Earth, to see what's happening on our planet. And of course, everybody is concerned about climate change, is concerned about biodiversity collapse. There are a lot of problems with pollution, so Earth observation is really a very important tool for policy and preservation of our environment. The first type of applications I will mention is monitoring of our atmosphere. Pollution is taking many lives in the whole world, so it's degrading the health of the population. One of the recent missions sent by ESA in space is called Sentinel-5P, the precursor for the Sentinel-5, with an instrument called TROPOMI on board. And TROPOMI is measuring, for example, the concentration of some pollutants like NO2 on that picture. And what you see here is a map of the pollution over Europe. The dark spot there, I don't know if you see my, yes, you see my cursor. This is Belgium. So this is not the best place to live in if you don't like NO2, right? Why is that so much pollution? It's because you have in Antwerp and Rotterdam big petrochemical industries that are producing a lot of NO2. So we can identify, really spot with this type of instruments the sources of these pollutions. On the right, it was mentioned already earlier, there is a new mission in preparation in Belgium called Altius to monitor ozone and other gases. And those missions require the type of mirrors that are pictured in the middle. Those mirrors are incredibly accurate. You cannot imagine how accurate they are. Basically, the roughness of those mirrors, that is the micro defects that we can allow when we manufacture those mirrors, is about 2 or 3 atoms high. We cannot tolerate more than this type of defects, otherwise the quality of the picture is not sufficient for the application. So it takes months and months to polish the mirrors that you see on this picture. That's our specialty in Liège. Okay, other type of application, of course, everybody likes to know what will be the weather tomorrow or during the weekend for the barbecue or the garden party or the sports that you're doing. Today, with Meteosat 2nd generation in orbit, we have about 5 days worth of weather forecast. Beyond that, it's not really accurate or reliable. There is a new generation of Meteosat in preparation in ESA. It's called 3rd generation, and it's going to give a lot more information about what's going on in the atmosphere. A smaller mesh with more parameters, humidity, temperature, wind, thunderstorms at different altitudes in the atmosphere. You feed that in a big algorithm software, and then you can have, hopefully we will have very soon, 15 days worth of weather forecasting, which is better for your holidays, right? But you can imagine also for a lot of commercial or industrial activities or military. So this is a part of one of these instruments that is currently being terminated or finished in AMOS. We are delivering the proto-flight of this back telescope assembly to our customer next month. I will go very quickly about ProbaV. It has been already mentioned twice today. It's a Belgian mission where AMOS has provided the 3 telescopes that are watching the Earth constantly. So the mission is to monitor vegetation over the whole planet with a low ground resolution, 100 meters at best. Every 2 days, we get a full map of the vegetation of the world with an accurate ground resolution of 100 meters. So very good to monitor, for example, deforestation, droughts, that kind of things. So ground resolution is one parameter that, of course, can vary very much from one mission to the other. And now we are very familiar with high resolution missions. Here you have an example of a high resolution small telescope that we are building for small satellite missions, new space market, which give better than 1 meter ground resolution. So they are, for example, in that application, able to monitor the health of single trees in the city of Brussels, for example. I'm going very fast because I have only 15 minutes and there are so many things I want to tell you. So I was talking about ground resolution. That's one important parameter, but it's not the only one. We have another very important parameter, which is spectral resolution. So to explain this, I will show you very simply a history of Earth observation. 40 years ago, we didn't have color pictures, only black and white.
This is called panchromatic. Okay, so you have one detector and it takes the intensity of the light, it mixes all the colors. Then a few years later, we put filters, red, green, blue, like on your television. And so with these three colors, we can recompose a picture in colors, which is very similar to what you see with your naked eye. That was about 30 years ago. Now, today, the state of the art is called multispectral, superspectral, and the benchmark in the world is called Sentinel-2. It's a Copernicus mission. It's delivering a wealth of data worldwide. Really, the reference, again, an ESA project, and all the optics of that satellite have been provided by AMOS. This is the state of the art, but this is not the end of the story. Tomorrow, this is what we are going to provide. Images called hyperspectral. With hyperspectral, what we do is slice the spectrum in very tiny slices, here 200, so that for every pixel of the picture, you have a complete spectrum. And so you can really detect in detail, what is it that I'm observing? What kind of crop, what kind of tree? Is the crop healthy or not? Does it need water? Is it being attacked by a pest? This is something that is extremely precious. And so I like to use this comparison. 20 years ago, a phone was used for only one thing, giving a phone call. Today, your smartphone is able to do hundreds, even thousands of applications. What we believe is that hyperspectral will do the same to Earth observation tomorrow. It will enable hundreds of applications because of the richness, the wealth of information it provides, very, very detailed. So just to illustrate what is planned in terms of hyperspectral in Europe, first of all, AMOS is developing an instrument that is now proposed commercially. It's a very compact instrument, actually much more compact than the competitors. It's going to be the basis for a very ambitious mission called SHIME. SHIME is one of the new Copernicus mission that is being planned by ESA. It's actually starting right now. We are discussing the contracts as we speak. And so this is going to provide this wealth of applications. I've shown here a few examples, but there are many, many more. Okay, so I have to stop here. I think I'm done with my time. I will be available after for any questions or further discussion. I just want to invite you to visit our website because it has already been said before, we are also hiring. We have for the moment 6 openings, but there will be probably 4 or 5 more coming in the next few weeks. And so you're most welcome to come and ask me more questions after the talks. Thank you very much.
So thank you, Philippe. So this was a very interesting, very interesting presentation. I think the people are quite cautious with the question. I could not see many questions on the chat. So I might leave the floor to, so there was only one question I could see from Jérôme, which was just asking you, Philippe, the lifetime that we expect of such an actuated mirror.
The mirrors themselves, they have a very long lifetime. From time to time, we need to, I'm talking about ground-based astronomy, we need to remove the coating and replace the coating. So it's cleaning and recoating, but you have mirrors which are in operation since 50 or 60 years. In terms of satellites, it's shorter because usually the limiting factor is the amount of fuel you have in your tanks for the propulsion system of the satellite. So usually satellites live 5 to 10 years, but ground-based telescopes can live 50, 60 years, no problem.
So thank you. I think we still have 15 minutes for the question. So first I would like to thank the speaker because I think for everybody you have really a broad, you had a really broad view of what we can say about technology in space. I think there are many things we could say. I could see one question from Tunisia, by the way, so about robotics, because it's true we didn't address really robotics much today, although that I think the docking system explained by Stijn can be seen as a type of robotic technology, because robotic is automatism, and I think this was addressed somehow in Stijn. And that's true that robotic is for sure associated to technology and associated to space. It's mainly for exploration, so for Mars. In ESA, our next mission to Mars was unfortunately not launched recently because of some technical problem with the parachute, but it's going to be launched in the next 2 years. And there you have rovers and robotics, like you can imagine. But I mean, there are many other technological topics we could address today. But I think thanks to the speaker, you had a relatively broad view of what is possible, a lot of what is possible in Belgium. So I guess it's quite impressive that you see what can be done and what is being done in Belgium. And I think Stijn mentioned it is true that Belgium is one of the biggest contributors to the European Space Agency. So indeed, a lot of big projects are being managed from Belgium. So I leave the floor to you, Marta, or to Dominic, maybe to have some question in the room.
Yeah, I was wondering if there were any questions around the people here present. There's a question. I'm gonna go there with the micro so you can all hear.
Okay, I have a question for Antwerp Space representative. I forgot your name. I'm sorry. You were saying that you had the communication system sent to the spacecraft, but where is the spacecraft actually made or developed?
So the question is, where is the spacecraft
being developed,
manufactured?
Yeah,
Now, generally for these very large missions, in contrast to the Belgian smaller satellites that you've made, like Probal 1, 2, and V, these larger missions are often made by one of the big prime contractors like Airbus or Thales. They're European groups with sites all over Europe, from Germany to France to Italy. And so for use specifically, so one model, because you always make an EM, which is a test model, let's say, that model was built in Toulouse. And so we went there in Toulouse, France, to the integration in that test model. And then the flight spacecraft was manufactured in Friedrichshafen in the south of Germany. And so we went there, and actually we still need to go there for some aspects to do the integration in the spacecraft there. But then for smaller missions, as I said, it is often, it can be done in Belgium.
Okay, this is better. When I was a student, I always dreamt of going to Airbus or Thales and be really part of these big missions. And I got the chance. I was working in Friedrichshafen and in Munich. But I've now also worked in a smaller space company, and maybe it's good to give a bit of the differences between the two companies. When you work in Airbus or Thales, you're hired for a very specific task. For example, you're responsible for a mechanism which has to deploy, and then the solar panel opens. This is what you will do for the next 5 years of your life. It will be only that mechanism. You will be the absolute expert in the world. If somebody needs a mechanism like that, they will have to come to you. So you will be the full responsible for that, and you will be given a lot of responsibility, but you will be very narrow. Within an organization like Airbus, it's very difficult to climb up and to be more broad. I think that's the beauty of being in a smaller company, whether it's a Belgian one or another one. You can be much broader, much quicker. And it depends a bit on what you would really like, whether you want to really dive into one very specific topic and stay there and be the absolute expert in the world, then definitely Airbus or Thales is your place. But if you want to be a bit broader, and you want to have the possibility to move around in a more flexible way, a smaller company can sometimes be a lot more advantageous. And if you want to only work with space, you have to do, or only work with paper, then you have to go to ESA and you'll be Michael, which only works with paper the last couple of years.
Any more questions in the audience? Micro is coming.
So Marta, there is a question on the, no, okay, we can leave the question in the, for the room.
Yeah, maybe let's take from the audience first and then we go to Q&A.
Thank you. So I was curious about what kind of technology do you use? So when we spoke about the mirrors, that you can reach an accuracy up to atomistic scale. So I was curious about how do you polish the mirror up to that precision?
I'm going to try to make a short answer for a complex question. So there are different technologies depending on the material. The first steps are mechanical. So either you are grinding the mirrors in the old-fashioned way, like we've done for centuries, but with more accurate tools, or you use new CNC machines, so numeric, how do you call this? Machining tools, okay? So that gives you the first level of accuracy. You are reaching a shape which is close to the final shape you want, okay? But then this is not enough, so you need to do some further polishing using different techniques like bonnet polishing. You have a complete range of different tools which are going to get you to, let's say, a fraction of a micron. But this is about 100 times too rough for the level of accuracy we need. So the issue with mechanical system is that if you want to continue removing material to improve your shape and roughness, you need to push on the surface. And only this little pressure is enough to distort the surface, and so you ruin the accuracy of what you're trying to achieve. And so the final step is called ion beam figuring. So you have to put your mirror in a vacuum chamber, remove all the air, and then you use a kind of an ion gun. So you accelerate the nuclei of some atoms, and basically you are sanding your mirrors. It's an image, it's a metaphor, but you are sending these atoms on the surface to remove atoms one after the other very slowly in order to reach the correct shape and the correct roughness. And this process is iterative. Between each operation, you have to go back outside, make measurements. Those measurements, again, you cannot do them mechanical. Mechanical is not accurate enough. You need to do them optical, so using interferometry. And so this iterative process, which is a very fast at the beginning, but very slow at the end, you are reaching a kind of an asymptote because you are at the limit of the physics, can take, let's say, even for small mirrors, sometimes 6 months, because you are reaching the limits of the physics. I hope I've answered your question.
We have a few questions here on the chat. For example, I'll go for the first one. Good evening. Can you please discuss the employment opportunities within the Belgium and broader European space industry for non-European citizens? Thanks in advance from South Africa. Any of the speakers? As a representative from QinetiQ myself, we have people from all over the world. So for QinetiQ, we have no problem. I don't know if other companies look into recruiting from other countries as well.
I think I can answer to that as well. I think there is no limitation. If you have the right degree, if there is the right mentality, there should be no limitation of where you're from. Of course, I don't know what could be any legal obstruction to be able to come externally to Europe to work. I'm not aware of what are the limitations there, but from company perspective, there is actually no limitation. Of course, if there are more like sensitive projects that are security related, there could be issues. But for most scientific engineering projects, I don't think there is an issue from the company point of view.
Maybe I will add one word to this. I think Belgium is a very nice place to live in, and the quality of life is quite good. One drawback that has been mentioned a lot in the past was the climate in Belgium, which was maybe one of the negatives, but this is changing as everywhere else. So we will be the winners of climate change. It's not funny, I know, but at least I must say that the people who are coming to our companies from abroad to work are usually very happy with the quality of life that we have here.
We still have more time for a few more questions. So I think this one is for Philippe. You explained how to fight air turbulence, seeing when looking up. Are there techniques used to improve angular resolution in Earth observation satellites?
Maybe this, I don't know if Michael wants to answer that one. I can certainly give my little perspective. So the instruments I know are static in space. So, but there is R&D ongoing to do some adaptive instruments. Basically, from what I've seen, they are mainly used in order to correct, let's say, the effect of launching the instrument because it has been aligned on the Earth. So with gravity, and also when it is orbiting the Earth, it's going usually from sunlight to shadow of the Earth. So you have thermal cycles, hot and cold, one after the other. And so we are currently developing technologies which are similar to active optics in order to correct those two effects, so the lack of gravity and the thermal cycles. In terms of adaptive optics, there is, I think, some thinking going on, but it's more difficult because if you want to correct for the turbulence of the atmosphere, you need to have a kind of a reference image where you can detect the influence of the atmosphere. So when you look at a star, you can use that star as a reference and correct the shape of your mirror. When you look at the Earth, it's more difficult because you have a scene which is precisely unknown. This is why you're looking at the Earth. You're trying to characterize the object you're seeing. So as far as I know, there is no adaptive optics system which is working, but I might not be aware of everything. Maybe, Michael, you want to add something?
No, I think you have a perfect answer, Philippe. The only instrument with adaptive optics I'm aware of is Gaia. So on Gaia, they had adaptive correction of the wavefront error, as far as I know. But indeed, what you explain is perfectly correct. So you do adaptive because you need a reference signal to, and then you can apply correction, but you cannot have it for Earth observation. So the only one I know is indeed the big mission for Gaia, where they had some adaptive correction.
There's another question here in the audience. We're going for the micro, 1 second.
Thank you. I was wondering, you just spoke about the possibility to work in your companies, but are you also open to do collaborations with institutions or other companies outside Europe?
As far as we are concerned, we do that all the time. So we have collaborations in the US, in China, in India, in Russia, so you name it. Not in Africa right now, unfortunately, because there are not so many projects there, but so there might be restrictions, but they would be imposed by the government, not by us. We are open to collaborate with every country in the world, almost.
Another question in the audience?
Yes, as a follow-up to your perspective on working for a big company or a smaller company in Belgium, what would be the disadvantage or advantage in working, for example, for ESA compared to working for a private company or smaller company in Belgium?
It's a difficult question to answer. I think my personal recommendation would not be to start working for ESA. If you want to work for ESA, do it when you've gained 15, 20 years of knowledge in the industry. That's also what ESA's role is. ESA is providing support, very good experts which can review
the work done by the industry. There are some very interesting projects which ESA organizes for YGTs. But I have the experience that if you do a YGT, for example, at ESA, where you're there for about a year, maybe 2 years, then you're perfectly prepared to take your step in industry, really do hands-on work within the industry. And then later on, if you want to return to ESA, there are plenty of opportunities once you have achieved the experience. Michael, if you want to add anything.
It's a very good answer. So yes, that would be my recommendation. I can talk from the ESA perspective. So on ESA side, we manage this mission that you have described. So first we set up these missions, and then we manage them. So it's a different work than what is being done in the industry. And as Stijn has explained, so you need to have worked in the industry before many years, so that you can manage, you can anticipate the problems, you can guide industry and so on. So it's a different job. So in ESA, we offer for young engineer, we offer a young graduate trainee, which is a 1-year program, so that you get in touch with our programs, and then you are sent back to industry.
Can I add to this? I myself worked 6 years in ESTEC, and I decided then to move to industry, which is not very common. I don't know of many people who have done that. The main reason was, and this is very personal, my impatience. Because when you work in ESA programs, usually they tend to be quite long, whereas in industry, the dynamics are more, let's say, nervous. So if you are the impatient type, you might think about that as well. On the other side, we also have projects that last very long in industry, so it's not an absolute. So the other maybe perspective is that in ESA, I think maybe the progression of your career is not as fast. If you are really good in industry, you can move very fast in your progression of your career.
I would also like to add something to that, because it's something that I can imagine many people wonder. You know, you want to do something in space, but we're Belgium. You know, what do we do in space? And actually, we do quite a lot. And even though we're sometimes not the one ultimately in charge, like for JUICE, for example, we will very often collaborate in all the interesting missions, just because. As you know, much of the funding is arranged through the European Space Agency. We being Belgium, commit a lot of money to this, more than, on average, more than the other European countries. And actually, that means that we can play an important role in all these missions, where we collaborate with large international companies. I mean, just to give an example again, for JUICE, so we are responsible for the communications subsystem. The satellite is made by a German-French company. Our components are coming from France, Germany, and Italy. And so you get to go to these places. You get to meet these other companies. So Belgium is in a way a very good starting point for a space career, because of the diversity of the ecosystem of the companies. And so I think either of the companies here, we are looking for people, but eventually there is always opportunity to, if after a few years you want to move somewhere else, you can go somewhere else, because there are opportunities. So don't think that the space career is supposed to be working in another country. You don't need to go to the United States to do nice missions. You can do it from Antwerp. You can do it from Liège. So there are opportunities in Belgium, I think. That's what I would like to add.
Thanks for all the questions. It's time. I'm sorry, there's still one question in the audience, but you can still approach the speakers, just not too much because of Corona, but you can still talk to them. And thank you so much for being here. Thank you so much to the speakers, to the chair, Michiel. Thank you so much for your collaboration. It was a pleasure to listen to you. And it's time to go. So thank you to all and see you tomorrow, same time, Switch to Space, topic 4. Bye.